Tree diagrams are a really handy way for us to organise the outcomes of a multi-step experiment, where we can have each step having a different set of branches. Now on this tree diagram I've put very little detail. I've said a restaurant has 2 entrees, 4 mains and 3 desserts. How many ways can I order dinner? Now I haven't even written down what those orders might be, but it's a helpful way of just thinking through the fact that there's going to be 24 different ways that I can order dinner. Clearly I've got a choice of 2 entrees, and if I make this choice, these are the 4 mains, these are the same 4 mains if I chose the other entree, and so on for the desserts. Now, the value of arranging information like this is that sometimes we only want to, focus our attention on one section of the graph. So even if you can imagine the whole tree diagram, sometimes you'll only need part of it, so you're building it in your mind and then thinking, no, I know I'm having this entree, so I can see that there's actually only these 12 choices up here. But imagining what's on the other side is sort of helpful. Now, you don't need to copy this down. I really just want you to have a picture of it in your mind so you've got an example of one of the ways that you could use it. Now, tree diagrams are actually much more useful when you can use them to calculate probabilities. And the simplest way to do it is when you're dealing with outcomes that are all equally likely. When that happens, there's no real need to write the probabilities on the branches or anything like that. We'll get to that next lesson. It's more a matter of seeing how many outcomes there are, because if they're all equally likely, and you know that there are, say, 8 of them, then the chance of any one of those occurring would be 1 out of 8. So in this example, a couple have 3 children. Find the probability that they have 1 girl. Now, it doesn't specify where in the family that girl would be, just 1 girl. So obviously they would have 2 boys. So if we lay out the options here, you can see that there's 8 of them, because each time they have a child, the possibilities double. So we've got 2 times 2, or 2 squared, and 2 times 2 times 2, or 2 cubed. If we had 4 children, there'd be 16 different possible outcomes. So all we need to do really is find the outcomes that have 1 girl in them. Here's where the girl is the youngest. In this one, the girl is the middle child, and in this one, the girl is the oldest, followed by 2 boys. If the chance of any one of these outcomes happening is 1 out of 8, or 1/8, then we can add them together, because clearly the fact that there's 3 of them makes it 3 times as likely to happen. And 1/8 times 3, or 1/8 plus 1/8 plus 1/8 is 3/8. So we've got 3/8 of a chance of having 1 girl. Now, it also makes sense then that there must be 3/8 of a chance that you'll have 1 boy and 2 girls. The probability of having 3 boys, 1/8. The probability that they're all girls, also 1/8. Now, you'll notice that 1/8 plus 1/8 for having all the same type, plus 3/8 plus 3/8 makes 1. And all of the probabilities have to add up to 1. And it makes sense also that each one is 1/8, and there are 8 of them. Now, knowing that these numbers, 1/8, 3/8, 3/8, and 1/8, come out really often is quite handy to know, because we get this sort of situation in lots of examples where there's a choice of 2 things. For example, in coin games or coin experiments where we can get heads or tails, and the chance of getting either one is exactly half, we end up with these same sorts of ideas. So if we toss 3 coins, or we toss 1 coin 3 times, same thing, the chance that we'll get, say, 3 heads, well, that would be exactly the same chance as the chance of getting 3 boys or 3 girls. It's going to be 1 out of 8. We can also use our knowledge of complementary events when we're dealing with tree diagrams like this. If we see that word "at least," then we know that we could use a complement. So if we're tossing 3 coins, the chances of getting at least 1 head would involve adding up all of the options that have 1 head, 2 heads, or 3 heads, and there'd be 7 of them to add up. We could reason that they're all equal and say it's 7/8, but we could also say it's 1 minus the opposite of getting at least 1 head. And the opposite of getting at least 1 head is getting no heads at all. So if the probability of getting no heads is 1/8, then all we need to do is 1 minus 1/8. And that's another way that we can get our answer of 7/8.